Hello everyone, today we are going to talk about waves on a dancing slinky, analyzing its forces and rotation. Our group studied the behavior of a slinky when it is placed vertically, boosted and then released. In this situation, two phenomena appear at the same time. First, the entire slinky undergoes a periodic torsional motion. Second, a lateral wave travels downward along the slinky. Most previous studies treated these two effects separately. Our central question, however, was how this torsional deformation acts as the driving force that generates and modulates the lateral wave. To analyze this, we modeled the slinky as a torsional harmonic oscillator. The slinky, experiencing two torques, elastic and frictional, oscillates torsionally back and forth. Notably, we predict the amplitude of the oscillation will decrease linearly due to column friction, and its period is almost constant. In addition, we modeled the slinky as a chain of rigid metal rings, connected by elastic links. Under small deformation and small angle assumptions, each ring can be approximated as a moving in circular motion. When projected laterally, this motion becomes simple harmonic motion. The phase delay between neighboring rings then give rise to a visible traveling lateral wave. Thus, we can predict the wave speed and the wave parameters related to coupling. We obtained three key physical results. First, the torsional amplitude declares linearly with time, while the oscillation period remains nearly constant. This indicates that the system is dominated by a constant kinetic friction torque, rather than viscous damping. We also find a good agreement in kinetic friction results. Second, lateral wave speed is independent of the initial number of twists. This agrees with the fundamental principle of wave physics. Wave speed is determined by the properties of the medium, not the excitation amplitude. Third, the wavelength is inversely proportional to the initial twist angle, while the frequency is directly proportional to it. This shows that torsional deformation sets the phase difference between adjacent rings, which in turn determines the spatial and temporal scales of the wave. Together, these results clarify the physical link between torsional motion and lateral wave propagation in the slinky. Thank you for your attention.